Hi, welcome to example 15 in our functions and graphs topic. So we've been looking at asymptotes and what that might look like in rational functions. What we're going to have a look at is to put it all together from your previous knowledge of graph sketching of polynomial functions. You know a bit about the drill. So to sketch a graph, we would normally already, be familiar with the idea of finding stationary points and their nature. And probably already the idea of finding the key kind of x and y intercept points to have a look at where intercepts exist. But the new thing that we're going to have a look at, we're going to add to our toolbox of graph sketching important points or lines are the asymptotes and their nature. So just before we go on to graph sketching, which is example 17 and 18, I'm going to have a wee quick reminder of the idea of finding the nature of stationary points using the second derivative, okay, as opposed to a nature table. So if you're happy with that, you can have a look at it or skip it. But what I'm really going to do with example 15 is not graph sketch just yet. What I'm going to do is go over the idea of using the second derivative as a test for the nature of a stationary point. So rather than using a nature table, the second derivative is a valid and often quicker way to work out if we have a maximum or minimum turning point. We know that the first derivative of a polynomial function or any function is what we call the rate of change of the value of the function, otherwise known on a graph as the gradient. So the first derivative is our gradient rule. It allows us to calculate the gradient for any value of x. The second derivative, we've been learning at the moment that it's about concavity. Okay, we did examples a little while back about concavity and points of inflection. So that's the rate of change of gradient. So what we're basically saying here is that if the second derivative is a negative value, okay, then that means that it's concave down. And concave down, okay, means that it goes like this. The gradient is becoming more and more negative. In other words, we've got a maximum turning point. And if the second derivative is a positive value, that means it's concave up, and which means that the gradient is becoming more and more positive, which means you get a minimum turning point. Okay, so we can kind of sum all that up. I'll get rid of that. That was just my mindless sketching. We can conclude this. If the value of the second derivative is possible, then we can deduce that it's a minimum turning point because we've discovered that it's concave up, and inversely, if it's a negative second derivative, then it's a maximum turning point. Kind of the I always think of the opposite. If the second derivative is positive, we tend to think of being up high or maximum. It's actually a minimum turning point. So it's the kind of opposite direction. Positive suggests high, minimum suggests low in that regard. Okay, there is one little note that I would also add, just a little caveat here. If the value of the second derivative is neither positive nor negative, don't panic, but we can't be sure of the nature of it. It could be a point of inflection, but you'll get that from a nature table, so you would go back to that resource at that point. So let's have a look at example 15. Investigate the nature of the stationary point of this function here. So I'm going to write it out. It says we've got f of x equals x squared plus x minus 12. I'm going to find the first derivative, because the first thing we still need to look at is where stationary points might exist, what values of x. And we've got 2x plus 1. Why is that of interest to us? Because stationary points exist when the derivative f dash x or f prime x is equal to 0. We've just worked out the f dash x is 2x plus 1. So our stationary points will be where 2x plus 1 is equal to 0. In other words, 2x is negative 1, x equals negative a half. So we're saying that there'll be a stationary point potentially when x equals negative a half. It says to investigate the nature of the point. It doesn't actually say to find the point, but I'm just going to go ahead and do it anyway. What's the y coordinate just for just now? Well, if x equals negative a half, then we're looking for the y coordinate. We're basically looking for f of negative a half, which is negative a half squared plus negative a half minus 12. Negative a half squared is a quarter minus a half minus 12, and that's going to give us a quarter subtract a half is negative a quarter, take away another 12 is negative 12 and a quarter, or negative 12.25. In other words, our potential or our stationary point is at negative a half, negative 12 and a quarter. Okay, now what we're looking really to do now is to find the nature of it, and you might have done in the past a nature table, but we're going to have a look instead at using the second derivative, and it's obviously useful when the second derivative is easy to find. If it's not easy to find, I would just stick with a nature table. Okay, you don't have to do it this way, but here you can see that the second derivative is very easy because the first derivative is 2x plus 1, so the second derivative is just 2. It's a constant term. Okay. Now what we're saying is that, remember what the determining factor was. If the value of the second derivative is positive, it's a minimum turning point, and very often it's still a function of x. We still have to put the value of x into it, but in this case here, it doesn't matter what value of x is. The second derivative is positive, so we can write here positive. So we can say it's a minimum turning point at negative a half, negative 12 and a quarter. Okay, and that's all we have to do. Okay, if we had still had a function of x, we would substitute x in it, and we'll do that in example 16. But that's a wee introduction to the idea of investigating the nature of a stationary point using the second derivative. I hope that's been helpful.